Have you ever wondered how contactless temperature sensors work? Devices like infrared thermometers and thermal cameras can measure temperature without ever touching the object. At the heart of this technology lies the infrared sensor, a powerful tool that detects heat and converts it into measurable signals. These sensors detect this radiation and translate it into temperature readings, making them essential in medical applications, industrial process, fire safety systems, and much more. But everything around us emits infrared radiation, and the hotter the object is, the more infrared radiation it emits. Guess which is the largest source of IR we have? Yes, it's the sun. But what exactly is infrared radiation? To understand that, let's take a step back and explore the electromagnetic spectrum. The electromagnetic spectrum consists of different types of waves, each with a unique wavelength and frequency. At one end, we have the radio waves, which have the longest wavelength. Moving up, we have microwaves, used in your kitchen and for communication. Then comes infrared radiation, which lies just beyond the visible light spectrum. Infrared waves have longer wavelengths than visible light but shorter than microwaves. Though we can't see them with naked eye, we feel them as heat. Now let's explore more on the most basic and most popular IR sensors we see. Now that we understand infrared radiation, let's take a closer look at how a simple IR sensor module is designed. The IR transmitter is simply an infrared LED that emits infrared light. This light is invisible to the human eye but can be detected by special sensors. When this IR light hits an object, some of it gets reflected back. That's where the IR receiver comes in. The IR receiver, which is typically a photodiode or a phototransistor, detects the reflected IR light and generates a small electrical signal. If no object is present, little or no light is reflected and the receiver remains inactive. But when an object enters the detection range, the reflected IR light triggers the receiver. Now, the electrical signal from the IR receiver is very weak. To process this signal properly, we use an operational amplifier functioning as a comparator. In simple words, the op-amp compares signal from receiver with a preset voltage. If the signal voltage is higher, op-amp gives a high output. But what if we want to adjust the detection range? That's where the potentiometer comes in. The potentiometer allows us to tune the reference voltage of the comparator. Finally, we have the LED indicators to give us a visual output. Power LED indicates whether the module is getting power through the VCC and ground. Signal LED turns on if an object is detected. To understand the working of this module, we need to primarily understand the basic functions of op-amp. The op-amp consists of inverting terminal, a non-inverting terminal, an output terminal, and to power up the op-amp, a VCC and a ground terminal. Now, let's see basic applications of op-amp. One of the most common uses of op-amp is an amplifier, where it increases the amplitude of input signal. There are two types, inverting and non-inverting amplifier. Here on the screen, what you see is a non-inverting amplifier, which implies that output signal is in phase with the input, or the gain is positive, and the gain can be measured by this given formula. Op-amp can operate as a comparator too. When op-amp is operating in saturation mode, which means the output can switch only between applied VCC or ground based on the input. If the difference between non-inverting and inverting terminal is greater than 0, or in other words, if V in at non-inverting terminal is greater than set point voltage at the inverting terminal, then output is equals to VCC. But if voltage difference is negative or V in is less than V set point, then output is 0 volts. Op-amp as an integrator. Yep, you heard it right. We can use op-amp to perform mathematical operations such as integration and differentiation of signals. The circuit shows an integration. A step input or a constant voltage is converted into a ramp output, but the slope is negative since input is given to the inverting terminal. Now let's focus on functioning as a comparator. Let's try to calculate the set point voltage at inverting terminal. We clearly see a voltage divider with two resistors of same resistance R. Hence, the voltage will be divided across both resistors equally and set point voltage will be half of VCC. So you see in graph, for any input voltage above the set point voltage, op amp will give VCC as output. Any voltage lower than set point voltage will have zero output. Now let's replace voltage divider by a potentiometer for the ease of varying the set point. The potentiometer is set at 50% position. Now let's try to change the resistance by turning the knob of potentiometer to, let's say, 25% or any random value less than 50%. We can see set point voltage is lesser than before, and now for the input voltage above the new set point voltage we have VCC as output. We can play around with the potentiometer to change the value of set point voltage and see or the output at the output terminal. Now let's try to understand the how IR sensor module is constructed. Here you see the op amp in comparator mode, IR transmitter connected to same voltage as VCC, IR receiver connected in reverse bias. Before trying to detect an object with the module, we need to associate a distance with set point voltage. Let's say we need to calibrate the sensor to detect an object when it is 5 cm from the object. First, we will position the potentiometer to highest position, that is high set point, place a dummy object at 5 cm, and now slowly try to lower the set point voltage with potentiometer. At one position, the LED turns on. The set point voltage at this position can now be associated with 5 centimeters. Now, if we try to move the object further away from the module, the signal LED turns off since we have a ground at the output terminal. If the object is brought nearer to the module, the LED turns on since we have a VCC at output. We can now use this calibrated module to interface it with external LED to indicate presence of object. You could easily replace this LED with relay driving a motor. This design is very helpful in sanitizer dispensers. Or you could replace LED with a buzzer. Or you can interface it with an Arduino to perform many other functions which are limited to IR sensor module itself. So that was it about the working of IR sensor. Hope you got a basic idea from this video. Stay tuned to learn more about many other sensors or how op-amp functions as an amplifier and many more topics. Thank you. Catch you in the next one.